Now, reactions involving cleavage of CO bond in alcohols. Now, the methods of preparation of one compound becomes the reaction of another family of compounds. Now, here the reaction of alcohols which involves CO bond breakage become the methods of preparation of alkyl halides. Now, PCl5, PCl3 and SOCl2 can react with alcohol producing the corresponding chloride, and if you use red phosphorus and iodine, we get the corresponding alkyl iodide, and if you use red phosphorus and bromine, you get the corresponding alkyl bromide. Now, one particular reaction is of importance in the case of alcohols, that is the production of alcohol from alkyl halide from alcohol. The reaction with the HCl and anhydrous zinc chloride. This reaction is called Lucas test. Now, tertiary alcohol can react with the concentrated HCl and anhydrous zinc chloride, producing an immediate turbidity. When a tertiary alcohol reacts with the HCl and anhydrous zinc chloride, the tertiary alkyl halide is produced. Whenever an insoluble compound is produced in aqueous medium, we get a milky appearance or opalescence. It is called OPALENCE, opalescence. Now, this milky appearance indicates the production of alkyl halide. You take a drop of oil, put it in water and shake well, you will get a milky appearance because oil is insoluble in water. Similarly, the alkyl halide is insoluble in aqueous medium. Now, HCl is 60% solution of hydrogen chloride in water, that is concentrated HCl. So, the medium is aqueous. Of course, anhydrous chloride is there. And since the medium is aqueous, the production of alkyl halide in aqueous medium produces a turbidity or a opalescence. A white turbidity is obtained. Now, tertiary alcohol immediately produces a turbidity. So, if an immediate turbidity is obtained, then we can infer that the alcohol is a tertiary alcohol. And the tertiary alcohols react by SN1 mechanism, and the SN1 reaction is faster than the corresponding SN2 reaction of tertiary alcohols, because in the SN2 reaction of tertiary alcohols, the transition state is highly crowded. So, SN1 reaction occurs at a faster rate. Now, secondary alcohols produce this turbidity on shaking for 5 minutes. This is because secondary alcohols react by SN2 mechanism, and the SN2 transition state is slightly crowded and contain two touched bonds. So, the SN2 transition state will be slightly higher in energy than the SN1 transition state. So, to attain this state, a little more energy is needed, and so on shaking for 5 to 10 minutes, then this transition state may be attained by a secondary alcohol, and it will produce a turbidity which is the result of liberation of the corresponding alkyl halide. Now, a primary alkyl halide cannot give a carbonium ion, and it definitely reacts with SN1 mechanism, and again SN2 mechanism, and again the SN2 transition state is slightly energetic, having high free energy, and so this transition state can be attained only by heating, so that the heat energy supplied is taken up by the substrate molecule to reach the high energy transition state. So, only on heating, a primary alcohol can give a turbidity. Hence, we can differentiate between these three types of alcohols using this reagent HCl concentrated and anhydrous chloride, and this combination of reagents is called Lucas reagent, and the test is called Lucas test. You please write down these steps. Now ROH reacting with the PCl5, we get RCl plus POCl3 plus HCl. Now 3ROH can react with the PCl3, producing 3RCl plus H3PO3. Now this acid is phosphorus acid. Then ROH plus SOCl2, we get RCl plus SO2 plus HCl. Now, so that is the reaction of alcohols involving CO bond cleavage. Now here red phosphorus and iodine, the mixture will react like phosphorus triiodide, so that 3ROH will react with PI3 producing 3RI and H3PO3. Now similar is the reaction with the red phosphorus and bromine. PBr3 will be reacting with 3ROH producing 3RBr and H3PO3. So I think I have written down these points. Now coming to the next reaction. It's again reaction in which CO bond is broken, that is dehydration reaction. Dehydration means removal of water from a compound by taking up the elements needed for the formation of water. That is, hydrogen and oxygen are the elements needed for the formation of water, and these elements are combined to form water and then removed. That is dehydration reaction. Now there is a reaction called drying. Drying reaction is a physical change where a wet substance is dried using heat. Now there water is remaining as H2O in the wet substance and it is removed as vapor. Here it's a chemical process where the elements needed to form water, that is hydrogen and oxygen, are taken up in the ratio as present in water and they are combined and then they are removed as water molecules. So we take down this statement. It is removal of 2H and O as H2O from a compound. Then alcohols remove H and OH as H2O in presence of concentrated H2SO4, H3PO4, anhydrous chloride or alumina. Now alumina is Al2O3. It's a dehydrating agent. So you write down this statement also. alcohols remove H and OH as H2O in presence of concentrated H2SO4, H3PO4, anhydrous zinc chloride or alumina. Alumina is Al2O3. Now, after writing these statements, let us see the reaction of elimination. It's a beta elimination where a OH group is connected to the alpha carbon, H is connected to the beta carbon, and H and OH are removed as a molecule of water. So we get a pi bond between alpha and beta carbons. This is the structure, that is ethene is formed, and concentrated H2SO4 at 440 Kelvin is used. So you please write down this equation. Now coming to the mechanism of dehydration. Now H2SO4 can ionize as H positive and HSO4 negative. Now here concentrated sulfuric acid is used as the catalyst. Now the reaction occurs in 3 steps. Step 1, that is formation of protonated alcohol. Now here OH is not a good leaving group, but OH2 positive is a good leaving group, because when that is removed as a leaving group by taking this pair of electrons, the positive charge over oxygen atom is neutralized and we get H2O molecule which is stable. So the lone pair of oxygen atom of OH group establishes a bond with the H positive. So we get an OH bond. So there is already an OH bond here. So 2 OH bonds. Then since lone pair is given for bonding, 1 electron of the lone pair is given to H positive and its charge is getting neutralized. And since 1 electron is removed from oxygen, oxygen gets a positive charge. So you write this equation, that is step 1, formation of protonated alcohol, and that is a fast reaction, and again it's a reversible reaction because this species can remove a proton and get back the free alcohol. So it's a fast reversible reaction. Now coming to step 2. Step 2 is the formation of a carbocation. Now I told you OH2 positive is a good leaving group. It can easily take up the pair of electron in this bond. So that is shown by an arrow starting from the middle of the bond and ending over oxygen atom. This means the pair of electron in this bond is entirely going into the orbital of oxygen. This bond is formed by the overlap of the orbital of oxygen and the orbital of carbon. Now the orbital of oxygen takes up both the electrons. So oxygen is getting an extra electron, that is the electron of this carbon. So its positive charge is neutralized and we get H2O. And here we get a positive charge, a carbocation is formed. And this carbocation is a primary carbocation. Now you take down these sentences and this equation also. Now this is called the rate determining step because it is the slowest step. Suppose you are starting from your home at A and reaching a place B, which is 8 kilometers away, and you walk for 2 hours, then your speed will be speed of walking. Speed of walking will be 8/2, that's equal to 4 kilometers per hour. And at B, some friend of yours pick you on his bike and reach the school C, which is 2 kilometers away, in 6 minutes. And 6 minutes is 6/60 hour, that is 0.1 hour. So speed of bike equals 2/0.1 hour, that is 20 kilometers per hour. Now total speed equals 8 plus 2, that is 10 by 2.1, and that is approximately equal to 5. Now total speed is approximately equal to the speed of walking, because speed of bike is very high. So that is the assumption behind the fact that the slow step is called the rate determining step, because the speed of the slow step will be equal to approximately equal to the total speed of the reaction. So it is called rate determining step, and the rate is nothing but speed of reaction, chemical reaction. Now we take down these equations and these statements. Now one of my doubts is that a primary carbocation is less stable, so it cannot be formed during a reaction as a free entity. But here in this mechanism, it is shown that a primary carbocation is formed. So that is practically, it is impossible for a primary carbocation, but under rare conditions it may be formed, I don't know. But we are using concentrated sulfuric acid, a highly polar medium, and we are using a temperature of about 440 Kelvin. So at this high temperature and due to the high polarity of the medium, it may be possible, I am not sure, it may be possible for this primary carbocation to be formed, or it may be possible for the transition state leading to the primary carbocation may be formed, because the transition state leading to the formation of primary carbocation will be very high in free energy. So the temperature and the polarity of the medium will favor its formation. That may be the fact. Anyway, it is a fact that a primary carbocation is not formed at all under any conditions. Now coming to step 3, removal of beta H as H positive in presence of the base. The base is needed for removal of beta hydrogen. This carbon is alpha carbon, this carbon is beta carbon. Now the hydrogen connected to beta carbon is called beta hydrogen, and here the base is HSO4 negative. Now in an acid, a base is usually protonated so that it is ineffective as a base. The lone pair of the base is combining with H positive, and its basic property or its nucleophilic property is destroyed by an acid. but the anion of acid, that is bisulfate, and HSO4 negative is called bisulfate ion, can function as a base. Now here an arrow starting from negative charge goes in between the oxygen here and the hydrogen, means an OH bond is getting to be formed. Now simultaneously this CH bond will be shifting in this direction between alpha and beta carbons. So the H positive from beta carbon will be combining with the HSO4 negative to give H2SO4, and this bond will form a pi bond between alpha and beta carbons, and we get the product. So these are the 3 steps. You write down this statement and this step. Now it is an observation that secondary and tertiary alcohols are dehydrated under milder conditions because the transition states in the slow step are lower in energy. So lower the energy of the transition state, lower the energy of activation, and lower the energy of activation, higher is the rate. Here again I am repeating 2 equations. K is equal to A by e raised to EA by RT, and rate equals K into concentration of substrate. Now EA is called energy of activation, and for secondary and tertiary alcohols the energy of activation will be small compared to the energy of activation for primary substrates, primary alcohols. And EA is lower, E raised to A by RT is lower, therefore A by EA by E raised to A by RT, since this is a low quantity, A by this quantity will be higher, so K will be higher, and rate is equal to K into concentration of substrate. For a given concentration of the substrate, that is alcohol, as K increases, rate increases, that is fact. So secondary and tertiary alcohols are dehydrated under milder conditions, and the reaction goes faster. So you write down these statements. Secondary and tertiary alcohols are dehydrated under milder conditions because the transition states in the low step are lower in energy. Tertiary alcohols definitely react by easy formation of a carbocation in step 2 because of its high stability, because of the high stability of the carbocation. Now, since stability of carbocations are in the order tertiary greater than secondary greater than primary, you know a tertiary carbocation is highly stabilized by plus effect and hyperconjugation, whereas the stability of secondary carbocation is decreased due to lesser number of hyperconjugation canonical structures and inductive effect, and for primary there is least hyperconjugation canonical structures and least amount of plus effect. So the carbocation stability is in this order, and so the order of reactivity of alcohols are also in the order tertiary alcohol reacting at a faster rate than secondary alcohol than primary alcohol. So you write down these statements. So milder conditions are needed for are only needed for elimination of water from secondary and tertiary alcohols. Here it's a secondary alcohol. It is 2-propanol. Now this is a beta carbon, this is a beta carbon, both are similar, so any one beta carbon may be chosen. Then the beta hydrogen combining with the OH group, removal of water, formation of propanene, 85% phosphoric acid and 440 Kelvin are used. So the acid is a milder acid than sulfuric acid. So you write down this equation. In the case of tertiary alcohol, the conditions are still milder, temperature is still lower, 360 Kelvin, 20% phosphoric acid. All the methyl groups are similar or identically placed, and hence any one S atom from the methyl group, any methyl group may be selected, removal of HOH, and we get a double bond here, and this molecule is, we number it 2-methyl 1-butane. So write down this equation. Now, one difficulty when concentrated sulfuric acid is used for dehydration of tertiary alcohols, for example tertiary butanol, was that the product alkene polymerized. You know what is polymerization? It is combination between simple molecules to form a large single molecule. That is the definition given. Now polythene, we are familiar with that. It is a polymer of hectene. A large number of hectene molecules come into contact, bond each other, and form a large chain of structure, and it acts as a single molecule, single product, and that is called polythene. So simple molecules like CH2 double bond CH2 reacting together, so say N molecules, we get CH2 single bond CH2 with valencies over this carbon, and N times it is called. Now we can see what is polymerization in these steps. So dehydration of tertiary butanol, if we are using concentrated sulfuric acid, the product is 2-methyl one butene. Now it will combine with an H positive, so this pi bond will be moving towards H positive. So we get CS2H, that is CS3, and a positive charge over this carbon. Now this carbon is now connected to 3 CS3 groups, so it's a carbocation. Now that is attacked by another alkyl molecule in this manner, so that this pi bond will be moving in between these two carbons, and we get a positive charge over this carbon, that is this structure. Now again another alkyl molecule will combine with this positive carbon through this pi bond, so that these two carbons are joined and we get a positive charge here. So we get this structure, and this may be extended by further reaction with such alkyl molecules, and finally a CS bond is shifting in this direction, so that this positive charge is getting neutralized. So removal of H positive is occurring here, and we get this structure. So the CCS3CS2, CCS3CS3CS2 group is repeated. This grouping is repeated to get a long chain. Now we can write down these equations if you understood it. Then write this structure of the polymeric molecule, and this is, you need not study these reactions, but it is better to remember these reactions, because you may be asked why concentrated sulfuric acid is not used for dehydration of tertiary-butanol. If such a question is asked, then the only answer is that the alkene polymerizes POLYMERIZEDS polymerizes to produce a polymeric structure, a molecule having a high molecular weight. So this is a simple molecule, it unites with itself and produce a large molecule, and that product is called polymer. And again, you need not study these reactions, but remember such reactions, and you take down these steps.